The broadcast is now starting. All attendees are in listen-only mode.
Welcome to our webinar, Telecom Interface Testing. Thank you for joining us. This webinar is being given by MET Laboratories. MET is a leader in the testing of electrical and electronic equipment for environmental hardiness, product safety, and electromagnetic compatibility. MET operates world-class labs in Baltimore, Maryland, Santa Clara and Union City, California, Austin, Texas, and also runs operations in China, Taiwan, Korea, and Italy. This webinar will run 30 to 45 minutes with an additional 15 minutes for questions and answers. Due to the number of registrants, all attendees will have their phones muted. If you have a question, please type it in the questions area of your GoToWebinar control panel. We will attempt to answer all questions at the end. If you are having technical difficulties, you can contact us the same way or call us at 330-418-9414, and we will try to resolve it quickly. Just a quick note on other upcoming events. In December, we're hosting a webinar on watt-hour meter testing and certification. You can register for events like this at www.metlabs.com. Today's webinar is being presented by Jim Reed and Camilo Obana. Jim is the director of MET's Telecom Lab and manager of MET's Meter Accuracy Lab. And Camilo is MET's EMC and Telecom Technical Manager. At this point, I will hand over the presentation to Jim.
Thank you. Hello, this is Jim Reed. I work out of the Baltimore office here at MET Laboratories. As just stated, I will be giving the presentation, about half of the presentation, and afterward I'll turn that over to Camilo Obana, my technical manager in our California office. And Camilo will take us home with some of the fiber and European requirements that we come across here at MET Labs. So getting into the presentation, you are attending the Telecom Interface Testing webinar. Okay, just looking at the agenda here briefly, it's a broad overview of telecom interface testing requirements for both the United States and Canada, basically North America, as well as international test requirements. So we'll be looking at interfaces and the applicability to various standards in those countries, as well as any critical testing, tests that are more problematic here at MET that we see fail more often, as well as some of the customer-driven test programs that we come across. So the overview of the telecom interfaces we'll be discussing, both for the U.S. and international, are listed there. You've got your analog, plain old telephone service type interfaces, as well as digital T1, your DSL type of interfaces, Ethernet, as well as your OC3 and so forth there on the U.S. side. The international, similar to what we test here in the U.S., but the E1, the ISDN, the DSLs, as well as the STM type interfaces we'll be discussing. So the applicable testing for the USA, Canada, and Europe, these are primarily the standards we'll be talking about. As you run down the list there, the Telcordia GR 1089 requirements, as well as the GR 295 core. Those are for the regional Bell operating company requirements here in the U.S. Anything being marketed, any equipment being marketed to the Bell operating companies in the U.S. would need to meet some level of testing out of those standards. The Administrative Council for Terminal Attachments, the ACTA TIA 968, is for end-user equipment. It's the traditionally known as Part 68 test program. So if you're selling a regular telephone or fax machine type of a product still. Wire line connected, it would need to meet criteria out of that standard and be applied to the active database of approved products afterward in order to market in the U.S. And very similarly, Industry Canada has a CSO3 test program for the same type of equipment. It's a very similar program to what's run here in the U.S. Then you have your ITU K.20, K.21, .44, and .45, basically for the telecommunications center installed equipment in Europe. Very similar but different set of requirements to what we have here with the Telcordia GR1089 core set of criteria. The ETSI, various ETSI standards covering the end user equipment, analog and digital equipment, and GR253 for SONET optical testing. So getting down into more detail about the testing for the U.S., for the utilities. Again, this is where you get into the GR1089 core testing. So any equipment that you're planning on selling to a Verizon or an AT&T, any of the regional Bell operating companies in the U.S. would need to meet some level of the GR1089 core criteria, as well as a GR63 core, but that's more on the environmental piece. And the focus here is on the interfaces. So essentially, any paired conductor interface port on that equipment would have some level of testing that would need to be performed on it in terms of lightning surge criteria or AC power fault criteria. And there are various tests in the outlined in the standard, depending on what type of port it is and where it's installed in the telecommunications network. So you've got equipment that could be installed at the central office location. You could also have equipment installed at a customer premise or a remote site. But if it's owned and operated by the regional Bell operating company, it would have some criteria that it would need to meet in order to satisfy the requirements of the standard. So there are also, depending on the type of equipment, outside plant ports, meaning it has a direct connection to the outside world, essentially, leaving the confines of the building and being exposed more directly to the outdoor elements, and an intra-building type of port, say an Ethernet, that would be run within the confines of the building. Obviously, in that situation, there's less criteria applied to that type of an interface, less energy in terms of lightning surge simulation and how that would couple onto those types of ports would be applied. But nevertheless, there are criteria for both situations. And the same is true for AC power fault. And the power fault is really simulating commercial AC power to some degree, being applied directly to the telecommunication ports on the equipment. Again, if you're plant type of a port, you're going to get higher levels of energy, 60 hertz energy simulating commercial power being applied to those ports, versus an indirect or an intra-building situation where you are less likely, that port is less likely to see those types of events occurring directly on the port. Some of the common failures that we see during the course of this testing: protection not adequate enough, secondary protection, that's gas tubes or transorbs that are designed right on the front end of the paired telecommunication ports not being sufficient enough to handle some of these lightning surge or AC power fault events. Fusing, in the case of AC power faults, can be a concern. At times, trace widths may not be large enough to withstand some of the energy that is applied to the front end of the port. And during the course of the testing here at MET, in the event of coming across a problem or a failure such as these that we're talking about, we would immediately stop test and notify the manufacturer or our customer of the situation and try to come up with some sort of a resolve to correct the problem before we get too deep into testing. So again, focusing on the GR1089 core for Regional Bell Operating Company compliance, there are several different types of ports that are outlined in the standard. And these are the actual definitions here, but briefly, a type 1 would be the central office located equipment with an outside plant port. So again, you have a direct metallic connection to the outside plant world. Type 3 is very similar to that. You've got an outside plant port, but you're located at the customer premise. Type 2 and 4 are very similar. Type 2 is an intra-building port. So again, your Ethernet is a very good example of that. A port that does not have that direct metallic connection to the outside world. Less testing is involved there. Type 5 is outside plant located equipment. Type 6, antenna ports. So if your device would have an antenna port on it, there's some criteria applied there. Type 7, AC power ports. There are lightning surge simulations performed directly on the primary side of the AC power port and be classified as a Type 7 port. And Type 8 is DC power. So once you just determine how many different types of ports you have on the equipment, and moving into the testing, you would determine what type of port you have, how many conductors are on that port, and you would go ahead and determine the connection arrangements to your test generators. So here, essentially you have 2-wire and 4-wire interface types, and you have differential and common mode connection arrangements depending on the test and the requirements set out in the 1089 standard. Here's an example of some of the outside plant lightning surge tests. These would be applied to, again, those ports that have the direct connection to the outside world. Test 2 is probably the most severe there, the 1,000 volt plus or minus 1,000 volt peak lightning surge, and these are the exponential decaying pulse type lightning surges with a 10 microsecond rise and a 1,000 microsecond decay. Some of the other lightning surges that would be applied to these outside plant ports. And here you have a set of intra-building lightning surge criteria. Again, those ports that do not have that connection to the outside world. You can see that the lightning surge simulations are much smaller in terms of the energy that are applied to those ports. But if, say, you have an unshielded twisted pair intra-building port, you would need to see the differential and the common mode applied to the conductors of that port. And you see the test connection arrangements there in the table that we saw 2 slides ago. Here is a sample of the AC power faults that would be applied to the outside plant ports. And there are first level and second level criteria that are applied to these ports. First level criteria, this is an example of what we have here, are less energy applied to those ports, but the pass-fail criteria is a bit more stringent in that the equipment must continue to operate properly before and after the surge event without being damaged. That's first level criteria. Second level criteria is more severe in terms of the energy that's applied to the port, but in terms of pass-fail criteria, you're allowed to sustain some damage due to the event. So you do not need to work and operate properly afterward, but you've got to fail safely. So no fire, no fragmentation, no electrical safety type hazard. So here are the ITU T Telecom requirements, very similar to the GR 1089, but this is what is required for Europe. The K.20 set of criteria is applied to equipment that's located at the telecom center, very similar to the regional bell operating company in the U.S. K.21 criteria is applied to equipment that is installed at the customer premise. So it's owned, it's operated by the telecom centers in Europe, but you have those two different locations, either at the center or at the customer premise or remote from the actual controlled environment of the telecom center itself. K.44 is essentially the test methodology for test 20 and 21, and K.45 is a bit different, looking at trunk lines going from a remote location to the CPE, the customer premise sites. So there again, any telco port or power port on the equipment would have some level of criteria applied to it, and very similar to the 1089 requirements. Essentially, there are lightning surge simulations for either intra-building or outside plant ports applied directly to those ports, as well as AC or DC power. Same sort of failures that we see with the 1089, as you would expect. The protection values many times are not quite adequate enough to handle some of the surge. Surges applied, and the corrections are there, either replacing the protection or sometimes having to respin a board to increase trace width. It's probably more common. Here are the applicable types of tests: symmetric ports, coaxial ports, dedicated power ports or mains ports, and differential or transverse are common mode surges are seen there. Primary protection is added or removed depending on the type of test that you're applying. And those numbers there are simply the section numbers out of the actual requirements standard. So here's a sample of some of those tests. Some tests have the primary protection removed. Those are a little less strenuous in terms of the energy applied, but there you've got to be able to handle those surges and not be damaged in many cases without the primary protection being applied to the front end of the telco port. Some of the more hazardous surges are applied through the primary protection. So that takes us into the active, the TIA 968D set of criteria. This is for the end user owned equipment. So this is your telephones or equipment that's not actually controlled by the bell operating company or the telecom center in Europe. This is owned by the end user. So we have the T1 digital criteria, some of the criteria that we look at there: clock accuracy, and make sure the repetition rate is accurate during testing, output power. There are lightning surge simulations that are required for this standard as well, and as well as pulse shape, either a 0, -7, or -15 dB line build-outs. They term them as shape A, B, or C. templates in this document, and leakage current or dielectric requirements are part of it as well. Some of the common failures: clock drifting, it's not accurate with the 1.544 megabit per second rate in the U.S. The equipment under test, the ET, not functioning normally after the surge. Transverse balance tests are performed to show that the lines are properly balanced above ground, or the pulse, the individual pulses taken as a screen's capture on a scope do not meet a criteria given in the standard for masking of that pulse. Many times their software adjustments are something that can correct some of these problems, particularly with clock rates, protection values, again with the surge testing. It's sort of a case-by-case basis depending on the problem. As I mentioned earlier, we will stop test if we run into an issue and contact the customer and sort of put our heads together to come up with a solution or a potential solution to the issue, hopefully not wasting too much time or getting too deep into testing. This is just a screenshot of the criteria for the transverse balance testing. You go from 200 hertz up to the 1.544 kilohertz in that case. A sample of the 0 dB line build out pulse mask. So an individual pulse would need to fit, for a T1 pulse would need to fit in that in the confines of that mask. Again, this is all for the TIA 968B standard for digital requirements. Now for analog requirements, very similar in some case, but there we've got the surge testing, signal power limitations. We're looking at a certain amount of DC resistance or during ringing. Again, with the transverse balance, we're making sure that the transverse balance criteria is met for the analog ports. And there are some masking and power spectral density criteria for any of the DSL flavors. It's termed xDSL there. Similar failures with surge testing. Sometimes the noise is a little too high to meet some of the criteria. Try to look at possibly filtering issues there in that case. Again, really the failures are a case-by-case basis, so we work with the customer to try to determine what is happening, what's causing the failure, and also suggest potential solutions to the problem. There is just a sort of an overview schematic of the lightning surge simulator used for the TIA 968B testing. They're showing the rise time and the decay time for both the open circuit voltage and the short circuit current waveforms. Some of the criteria for the analog signal power in the various bands across the spectrum up to 266 kilohertz. And just a basic schematic for the transverse balance test circuit. And again, there are criteria for the analog, for the transverse balance. It's the same criteria, the same mask that's used for the digital as well. And here's some of the power spectral density requirements, depending on, and this is showing the ADSL or the extended ADSL2 limitations for both the dBm per hertz as well as the power within a 1 megahertz sliding window. So you see the frequency bands there on the left, And essentially, depending on the type of DSL that you're looking at, there are different masks, different limitations across the frequency spectrum here that need to be met for the different DSLs. There's one for Vdsl. And that's it for my part of the presentation. Now I'll turn it over to Camillo. Camillo can go over the analog criteria as well as the more of the European flavor test.
Thanks, Jim. Yeah, so this particular test right now is the GR253 core, which is dealing with the optical interfaces such as OC3, OC48, OC182, and OC7068. This is just for the U.S. market. The next slides down will be dealing with purely the international market. For the GR63, some of the most common failures, 253, most common failures we always see is that the eye diagram and extinction ratios do not meet the masking. The clocking source of the EUT drifts beyond the specification. The EUT puts out too much jitter that exceeds the limits. Clock sources drift more than allowable for a 24-hour period for their wander. And the EUT cannot handle the amount of jitter being applied to the product. The most common fixes for those that I've seen are just mainly software and firmware adjustments. This is really simple, easy to fix. Like for your jitter, some people forget to turn on their jitter attenuator, or they pretty leave it off. So these are the most common fixes that I've seen correct the issues. This is basically the slide, the diagram of a mask for a sonic OC1 through OC12. This is just a sample of where the eye diagram should be. The eye diagram of those interfaces shall fit within the mask tolerances that are given in the bottom table. Next. This is the maximum attenuation and range values for the optical interfaces, OC1 through OC48. As you can see there's two different wavelengths tolerances. There's a 1310 nanometer and a 1550 nanometer. So if you use those type of SFPs for long range or short range, this will give you the table where your maximum attenuation should be and your minimum attenuation. Next. These are the optical parameters. So for OC1 to OC48 optical interfaces, these are the operating parameters of that optical link. So the optical interface should meet these parameters during tests. So for example, the interface should have a maximum, should be able to operate between 1260 and 1360 nanometers for OC1 interface, or for due to the variance of the SFPs. And for example, OC48 should operate between 1266 and 1360 nanometers. Next. This is the diagram of the tolerance of the wander deviation. So basically what we do is we apply the clock into the EUT, and we verify that the clock does not drift more than the specified limit within the standard as per this graph over a 24-hour period. Next. These are just the time deviation values, part of the wander testing. These are actually the limits for the tests. Next. This is the category 2 jitter transfer mask. So this is actually showing you the limit for the interface, for the optical interface, so that for example, the OC12 interface cannot exceed the certain amount of jitter being transferred out of the unit. So basically, the EUT should not exceed not exceed the limits. Should not exceed the limit by outputting more jitter than what's within the mask tolerance. Next. This is sonic category 2 tolerance jitter mask. So basically, the EUT shall be able to accept certain amounts of jitter and not become interfered with the limits within the standard. Next. These are jitter generation. So based on this table here, this is showing that the EUT, for example, OC12 shall not generate more jitter than what's within the limit. So for OC12 between 12 kilohertz and 5 megahertz, the EUT should not put more out than 1.1 UI PP and 0.01 UI RMS noise onto the, generate that much jitter onto the line. Next. The next following slides will be dealing with, test standards for the international market. So we have the European version, ETSI ES 203.021, almost similar to ACTA 968. We have TBR 12, TBR 13 for E1 digital equipment. We have Australia's ACF SO16 for E1 to E4 digital equipment. We have the New Zealand TNA 117 for E1 interface to E4 digital equipment. And then the K20, K21, K44, and K45 is part of the international standards list, which Jim discussed earlier. Next. And then we also have the Hong Kong 2028 for T1 digital equipment. And then we have the ADSL version for the European market, G992.1, for Vdsl, G993.1. And then we're doing the ITUT G703E for E1 and E4 digital equipment, T1 TBR 24 for E3 digital equipment. And then you have the ITUT G707 for optical equipment, G824 and G957. Next. So basically optical testing for analog TE. So for this would be the equivalent, so the ETSI ES 203.021, which deals with analog POTS lines. The majority of tests are similar to ACTA, but with some variances and different frequencies. We have DC unbalanced earth, DC resistance, sending level 10 megahertz, DTMF, where we're measuring the high and low frequencies of the digit dials for POTS. We're measuring for DC current. We're measuring the current being the DC current of the device, and then you have frequency combinations. Next. Some of the common failures that we see with this test are that the EUT's impedance is unbalanced and it exceeds the limit. The impedance between tip and rings less than 4 megohms were measured using specified voltages as per the documentation. The output power of the tones exceed limits. The power of the DTMF signals exceed limits. The DC current during ringing, which was set at 25 hertz and 50 hertz, the voltage 90 volts exceeds the specified limit. And then the frequency combinations exceed limits when you're measuring the high and low frequencies to get the digit. Some of the most common fixes here are to adjust the internal impedance of the tip and ring circuitry, modify the software and chipset registry, adjust internal impedance, and modify software and chipset registry. So some of the fixes are pretty much similar. This is for a sample of analog unbalanced earth, kind of like longitudinal balance in ACTA Part 68. Next. This is analog. This is the diagram of analog 10 hertz sending signal level. So we're putting a 10 kilohertz signal into the line, and we're measuring the noise being outputted on the pots. Next. These are the frequency combinations. So when we're measuring the combinations, we're measuring the digits. So when we measure the digits, like for example, 1 digit, we're making sure that you're getting 197 hertz in low group, and then your high group would be 1209. To make sure when a person dials the digit, they get the right number being presented onto the POTS line. Next. This test deals with the international digital testing portion, which is the TBR 12, 13, Australia SO16, the New Zealand 117A 117, Hong Kong 2028, ITUG 703, TBR 24, and TBR 3 and 4. So for the digital section, E1 and E3 and ISDN, some of the tests that we'll see for these tests that are common to these standards, pretty much similar, but different different criteria, meaning different limit values, but the testing is pretty much identical. You would have waveform generation, jitter generation, wander. Like I said, we'll measure how much the frequency drifts over a 24-hour period. Jitter transfer. We're making sure how much jitter we're measuring how much jitter you're transferring off the line. Return loss, clock accuracy. You're making sure that the clock of the interface is within tolerance. We're making sure that the frame structure of the interface is correct. And then some of the layer 2, layer 3 verification for handshaking, communication, for the additional testing for ISDN. Most of these tests are the physical layer test, which is layer 1. Next. Some of the common failures of these tests is that when we're doing the pulse shape masking, for example, for E1, the pulse does not meet the mask. It exceeds the mask. Some of the problems we see is the jitter from the EUT exceeds limits, the EUT generates too much jitter, or the clock source wanders beyond specification with a 24-hour period. Most of these common fixes are mostly common, are pretty simple. Mostly it's updating software, modifying jitter attenuator settings. So it's pretty much those two common fixes. Next. This is a diagram of a sample E1 mask rate at 2048 kilobits, which is E1. As you can see that when we measure the mask, that the pulse has to be centered within the mask and fit within the mask and do not exceed the outer limits of the mask. Next. This is the graph for the input or output jitter measurement. So we're measuring how much jitter is being actually outputted of the EUT. As you can see, that's a table that gives you the specified amplitudes of the jitter being allowed. Next. Next, we're dealing with the Vdsl and Adsl testing, which is equivalent to the ACTA 968 testing. This is just the European version of it. So some of the tests are pretty much common, what you see, which we will perform in the US test for these interfaces. The pulse, PSD, you have power 1 megahertz sliding window, aggregated power, DSL output characteristics, and electrical characteristics. Next. Some of the common failures for this testing is that, for example, the masking, because we're measuring the output power mask of the Vdsl or DSL interface. So we have the mask criteria that it needs to meet. So when we put the power, the modem in a full spectrum mode, that mask must be able to fit within the specified masking of the test. The power level in a 1 megahertz bandwidth exceeds the limits, and the aggregate power exceeds limits. Most of these fixes can just be updated. Usually, like I said, this is layer 1. Physical layer testing can be fixed by updating some of the making software or firmware changes to the product. Next. This is a mask for the ATUTC transmitter of a PSD mask, pulse spectral density mask. So, like I said, what we'll do is we'll put the product in various output power modes, and we'll make sure it fits within the tolerances. Next. This is the AUT receiver transmitter mask, and this is what the output power for the remote side. So when we put it in full power mode, like for example, if you had a ADSL modem at a customer site, that would be considered a ATUR, and then we'll basically put that in full spectrum mode, and then we'll measure the pulse mask and make sure it fits within the tolerances. Next. These are actually the limits and bandwidths of how to calculate the mask. Next. This is the masking of a Vdsl interface. So same type of concept. If you had a Vdsl modem, we'll put it in the full spectrum mode, look at the signal, try to fit it within the mask tolerances, and if it comes outside of the masking, then some type of software firmware adjustment is needed to make it comply, to make the signaling fit within the mask. Next. The next thing we'll be dealing with is the optical version of the GR253. It's pretty much similar, except you're dealing with the different rates than the US. So this time we're dealing with the ITU-TG 703, which is ITU-TG 824, ITU-TG 957. These deal with STM1, STM3, STM12, STM64, and STM256. Most of this testing, even the US GR253, follows these ITU-T standards as a guideline. So most of these similar tests that you'll be doing for GR253 can be covered for Europe, but some of the testing for Europe has an extended range that you would need to cover in addition to the GR253. So you have frame structure, alarms, output clock, jitter generation, jitter transfer, wander, mask, and distance ratio. So like I said, these are the same bulk of tests that you'll see in GR253. Next. So like for the same type of common failures you see in like doing GR253 is the optical frame does not meet the requirements. The UT does not initiate proper alarm status when alarm is ejected, like your AIS alarm or your LOS alarm. EUT, internal clock to see is allowable just more than 50 ppm. This is the ATU clock. The EUT generates too much jitter. So yeah, for example, the same type of fixes would be the software firmware updates and modification to the jitter attenuator to pass the jitter tolerance testing. Next. These are the parameters for specified STM optical interfaces. So depending on if you're short range, long range, and whatever criteria that you're going to be specified under, you have to meet these type of your product needs to meet this type of characteristics. Next. For example, this will be the eye pattern mask. This is actually, you can see it's the same. You just have the eye diagram, the mask, the eye of the interface, the optical interface. When you're measuring the signaling, has to meet within the masking. Next. So this is the wander limit. So basically for European, for 2048 kilobits, the EUT should not exceed the specified wander limits over a 24-hour period. Next. This is the tolerance maximum jitter for interfaces. So when you measure jitter, the EUT should not exceed more jitter than which is in the specified limit. So for example, STM4, between 1 K to 5 meg, the EUT's peak amplitude for jitter should not exceed 1.5. And from 250K to 5 megahertz, the peak amplitude jitter should not exceed 0.15 UIPP. Next. This is the input tolerance limit. So basically the EUT shall be able to accept this amount of jitter being tolerated to the EUT. So it cannot exceed, it should be able to exceed the graph. It shouldn't go below the graph. So for example, if the limit, for example, at let's say 1 kilohertz, it should not exceed 0.15 UI. Next. These are pretty much it of the presentation, but this is some of the useful websites that you can look at and get standards or information that is what the RBOC requires, or the RTTE or the ACTA telecommunication requirements. Next. And thank you. Any questions?
That concludes the presentation portion of this webinar. Tomorrow, an archived copy of the webinar will be available on metlabs.com. We will send a follow-up email with a link to this file. Now we will answer questions. If you have a question, please type it in the questions area of your control panel. For questions we can easily address now, we will read the question aloud, then give the answer.
So one of the questions that I've seen here is one of the questions was that does the international regulatory testing for the digital interfaces such as the E1 or through E4, for example, the TBR12, TBR13, or the TBR24, do they follow some of the similar testing as I2GG 703? Yes, the answer is yes. I2G 703 basically does have the similar requirements as in the TBR12, TBR13. However, some of the standards that are there, TBR12, TBR13, may have a little bit higher limits, but they follow the same test procedures.
If you have additional unanswered questions, please contact us via phone or email. Tomorrow we will send a follow-up email that will include a link to the presentation. That concludes our webinar. Thank you for joining us today.